All right. Hello, everybody. We're going to give folks a few minutes to join the webinar, and then we will get started. Thanks for joining us today. Great. Well, I'm going to go ahead and kick us off since there are a lot of folks here right on time and want to respect everyone's time. And we have a relatively short hour to talk about a lot of important topics. So I think we can go ahead and dive in. By way of introduction, I'm Sarah Baldwin. I'm a senior director within the electrification team at Energy Innovation. And for those unfamiliar, Energy Innovation is a research policy firm and think tank, and we provide recommendations and research for policymakers to inform their decision making on climate and clean energy policy. And today we are having a roundtable discussion and webinar on the topic of grid reliability in the clean energy transition. And I'm already doing the welcome, and I'm going to do a brief overview of Energy Innovation's new report, which is sort of the impetus behind this webinar. And then we will pivot to our roundtable panel discussion. And that will be moderated by Michelle Solomon, who's my colleague at Energy Innovation. And then we will carve out time at the end of this for audience Q&A. Would love for folks to, as you have questions, put your questions in the Q&A box. You can use chat as needed for any technical issues, but we're trying to funnel the Q&A to the Q&A box so we can track the questions that come in. Great. So kicking us off here, as I mentioned, Energy Innovation authored a report in February, late February, called Grid Reliability in the Clean Energy Transition. And this report was really intended to be a primer on this topic. We wanted to cover not only the basics of planning and operating a reliable grid, but really wanted to dig in on some of the topics relevant to the clean energy transition. As we know, this is an issue that's coming up more and more people are concerned with grid reliability, but a lot of folks don't necessarily have the background and technical understanding of some of the fundamentals of grid reliability. So we wanted to pull together the growing field of research and draw on the expertise of many grid reliability experts and put it into a one-stop shop resource for policymakers and non-technical audiences alike to be able to better understand some of these nuts and bolts of reliability. And as listed here on the left, we have the different chapters which cover the core topics within the report. And we also have a very handy key terms document, which can be helpful whenever you're having a more technical conversation and want to remind yourself what it is that fast frequency response actually means and what reactive power actually does. And then we also have a separate key takeaways and policy recommendations document. And, you know, at the end of the day, we really want this to be a resource to help demystify the truths and misconceptions of clean energy and their ability to provide reliability services and support a very robust, secure, and reliable grid. And we acknowledge there are challenges in getting to that 100% clean energy future that is ultimately the goal to bring down emissions and mitigate climate change. And then we also provide policy recommendations to ensure that the transition from where we are today to the 100% future is as smooth and as manageable as possible. So we encourage you to go to our website, energyinnovation.org, download the report, and you can also access any of our research there for free. And as I mentioned, within the report, we actually interviewed several grid experts and have a great group of peer reviewers who took a look at this, listed here in no particular order. Michael Milligan, Dr. Michael Milligan of Milligan Grid Solutions, Rick O'Connell and Priya Sridharan, of Grid Lab. Rick is here today with us. Allison Silverstein of Allison Silverstein Consulting, and I believe Allison is one of our attendees today. Derek Stenklick of Telos Energy, Wilson Ricks also here with us today, and then three of our colleagues at Energy Innovation, Eric Gimon, Michael O'Boyle, and Brendan Pierpont. So really want to give a huge thanks once again to these folks, and definitely appreciate all the feedback we received throughout the report's creation. So just to kind of set the tone for this conversation today, we recognize that the term reliability is thrown out a lot, and not always accurately and or correctly in terms of what we're talking about. So just to remind folks that reliability is actually a characteristic of the entire electricity system, and individual resources contribute to reliability as part of a balanced portfolio, much like a mutual fund or balanced stock portfolio. And that has always been the case, and that will continue to be the case. So whenever you hear someone talking about the reliability of a single resource, that should raise a flag that is not necessarily grounded in full truth. The other three components of reliability are actually interrelated components, which we'll talk about more today. First and foremost, resource adequacy. This is the longer term dimension of reliability. This is planning in advance to ensure that we have enough supply to meet demand. And we're hearing more and more that demand is growing, we need more supply. That's what we're talking about when we're talking about resource adequacy. Operational reliability is more of the short-term dimension. This is the day-to-day balancing of supply and demand in real time to maintain the frequency and the voltage within safe operating limits. And this is the world of grid operators and is incredibly important throughout all of our day-to-day lives. We often do not have any disruptions whatsoever. We have a very reliable grid, and that is because we have great tenets of operational reliability in place. And then lastly, resilience. And this is tied to grid reliability, but it is a separate concept, and that is basically the ability of a grid to ride through an extreme event, such as extreme weather, polar vortex, and then recover quickly and bounce back. It also includes grid hardening and operational solutions that are part of maintaining a grid. And as I mentioned, another or kind of a subset of the operational reliability piece is essential reliability services. And these help maintain the balance of supply and demand in real time. And they fall into three primary categories. And I'm not going to describe these in detail, but they are described in more detail in the report. So I encourage you to take a look. But basically, it's voltage support, frequency support, and balancing and ramping. And these all kind of work in a kind of a symphony, if you will, of different resources providing different components and characteristics that provide all of these throughout a day-to-day as well as over the long term and in response to any extreme events. And then the third and final component to the report that we really want to emphasize here is that we often put a lot of emphasis and onus on the supply side resources for good reason. We need a lot of robust and diverse supply to provide the energy needed for demand, but we also have a toolbox full of demand side solutions that can and should contribute more to a reliable grid. And there is an interplay between those two that connects between the distribution system and the transmission system, the bulk power system and the distribution system. And arguably there's a lot more that can be done to make sure the demand side is really pulling its weight, especially in a time of demand growth. So with that, I'm going to turn the time over to Michelle, and she's going to kick off the webinar.
Awesome. Thank you so much, Sarah, and thanks for that wonderful intro on some of these reliability topics. And I'm really excited to moderate the panel discussion with the experts we have on the call today. So I'm Michelle Solomon. I'm a manager in our electricity program at Energy Innovation. And today we have joining us Rick O'Connell, who is the founding executive director of Grid Lab, where he leads a team of experts providing comprehensive technical grid expertise to policymakers and advocates. We also have Julia Matavoisian, who is the Associate Director and Chief Engineer at the Energy Systems Integration Group. She has more than 20 years of experience in the power industry and prior to joining ESIG, Julia was the lead planning engineer of the Electric Reliability Council of Texas, or ERCOT. So excited to have her grid operator expertise on the call. We also have Wilson Ricks joining us, who is another one of our experts on the that we interviewed in the report. And he's a postdoctoral research at Princeton University, where he applies macro energy systems modeling and other tools to assess the role of policies and technologies in electricity systems decarbonization. So with that, I will turn it over to our panelists for some introductory remarks. So we'll start with Rick.
Oh, great. Thank you, Michelle. It's awesome to be here and with such great folks on the panel as well. I think Sarah did a great job of sort of introducing what we're talking about, but I'll just sort of build on that a little bit because reliability is kind of this broad term that means a lot of things to a lot of people. And really, I think from the customer perspective, most outages are actually failures of the distribution system. So those are the wires that carry electricity to homes and businesses. And there are very few outages that, because we don't have enough energy in the system to serve everyone. And I think that's kind of a growing concern. And I think that's really what we're here to talk about today. And as Sarah mentioned, we call that resource adequacy, and it really means, do I have enough generating capacity? Do I have enough fuel? Do I have enough energy in the system to meet demand at all times? And so we think about this resource adequacy in the planning time frame, right? So we got to plan in advance, 10, 15, 20 years in advance to make sure that we have enough energy in the system. So when we get to real time, we can actually meet load. And so, of course, Julia, I think, is going to focus and talk more about the operational reliability. And, that's important. Like, you can't sort of decide day ahead. You're like, oh, we need some more energy. I'm going to rush out and build a new power plant. These are long lead time things. I think really what's going on right now, the sort of current moment that we're in, is that there's two trends that are colliding. The first, that we've really been moving away from generating electricity from coal, which used to supply sort of 40% of our electricity and is now kind of down in the mid-teens. And we've really moved towards wind, solar, and natural gas. And so that really means we have a lot of generators that rely on the sun and the wind to generate electricity, as well as generators that rely on fuel, natural gas. And so we really have to plan carefully to make sure that we have enough energy to meet load in all hours. And then I think the second trend that we're all sort of aware of, right, is that load growth is really surging for the first time in a couple of decades. And this is really due to electrification, new manufacturing. And I think, of course, like the sort of big elephant in the room is data centers. And so I think that these two trends sort of colliding at the same time is that a lot of utilities and grid operators and their regulators are getting a little nervous, right? They're getting a little concerned that we're not going to be able to have adequate resources to meet this growing load. I actually don't think that concern is valid. I think we can do both. Like, I think we can walk and chew gum at the same time, right? We can both grow the clean energy percentage of our electricity and grow the amount of load that we meet to meet certain demand. These are not mutually exclusive goals. And so I just want to point out a few facts. First, we've got, the majority of the generating capacity that's waiting in our interconnection queues to connect to the grid and provide energy. The overwhelming majority of those are wind, solar, and batteries. And I mean, just the last couple of years, the overwhelming majority of the resources that we've connected. So last year, we installed 50 gigawatts of new resources, which was a lot. 93% of those were solar, wind, and batteries. This year, EIA says we're going to install about 63 gigawatts of resources. Again, a lot. I think that's close to a historical peak. And again, 93% of that is wind, solar, and batteries. And coal is going to continue to retire. I think there's an incredible story coming out of Texas, right? So over the past decade, Texas has grown its electricity generation by 36%. It's now the largest grid in the country, largest state in the country in terms of generating capacity. And while it grew that electricity generation, it also doubled its share of carbon-free energy from 23% to 42%. So Texas is really showing that we can do both, right? We can decarbonize and grow our grid. And I'm sure Julia is going to talk about what's been going on in Texas. Like the last couple of weeks during the day, Texas has been running at 85% carbon-free for the last several weeks in the spring. And it's not just Texas, right? SPP, the grid that stretches from the Dakotas to Oklahoma, ran at nearly 50%, ran 47% carbon-free last year. Many hours of the year, SPP runs on 90% wind power. So I think it's really clear that we can do both, right? We can meet growing load with clean energy at the same time. And then I also just want to mention, and I think both, Sarah did a great job of teeing this up, but we're talking, we don't want to just focus on the supply side. We should also really be thinking about the demand side. We just have this much more sophisticated communications and control systems here in the US now. Like, it used to be very hard to sort of have load that was responsive to price or other kinds of signals. But now we've got smart thermostats, we've got customer-sided batteries, we've got EV charging. Really, this is load that can be controlled and respond to market signals. And, I think this is a really important way that we're going to be able to meet our reliability. It's not just on the supply side. So that's it for me for an intro. I'm love to hear from our other amazing panelists, and look forward to the questions that you're going to throw at us.
Awesome. Thank you so much for that overview, Rick. It's great to hear from you about how not only clean energy can be reliable, but it is reliable, and grids are currently relying on it today. So with that, I will turn it over to Julia to talk about some of these operational reliability aspects. Oh, I think you're muted, Julia.
Yeah.
Awesome, we can hear you.
And Michelle, I'm seeing the slides pretty small. I'm not sure if you can make it bigger.
Can you switch?
It looks like, yeah, like switch to presenter mode.
It's, oh.
Yeah,
Perfect.
there you go. All right, yeah, so I wanted to hit on a few points with regard to this reliability node that you have and essential reliability services. I'm glad you brought up that term. I'll probably going to touch on some of the keywords that you have in your glossary. So if you just kind of focus on this chart on the left-hand side, I want you to walk through short history of inverter-based resource integration into power systems. And when I say inverter-based resources, I mean solar, wind, and storage, battery storage, because they're interfaced with the grid through power electronic inverters. And so that's how the term inverter-based resources is collectively being used for this. So to say wind, solar, and storage. So what you see on this plot, this is just a cartoon. It's not, it's not a plot reflecting something real, but just to illustrate what's going on. On the left-hand side, on x-axis, you see strong grid. You often hear this term strong grid. What it refers to is the grid that is currently powered by synchronous generators such as hydro, coal, nuclear, gas-fired generation. And on the right-hand side, you see this term weak grid. It often refers to parts of the grid that are far away from this traditional synchronous generation and have a lot of inverter-based resources such as wind, solar, storage. What you can also see is percent there is instantaneous percent of energy produced by inverter-based resources feeding load at the time. So in any given instance, this percent of load been fed by wind, solar, and storage resources. And then on y-axis, kind of anything going lower towards x-axis is unstable, and everything going towards the top is stable. And so what we're talking about here is as we progress from 0% of inverter-based resources instantaneously on the grid towards higher percentage of resources. Initially, when we had very few inverter-based resources on the grid, we didn't ask for them to do anything. So they were just there to produce megawatts, and we were testing out the technology, and it was just, come and produce megawatts. Over time, as we got to maybe 10-20%, it became necessary and essential that these resources stay connected when there is a disturbance on the grid. So not only they should produce megawatts, but they should also continue supporting the grid when there is a disturbance or fault or something, happening on the grid. Then as we progress even more, these resources start displacing, as Rick mentioned, say coal-fired generation that traditionally has provided some of essential reliability services. So then it becomes important not that they only stay online, but they also provide some services to the grid that synchronous generators provided before. And so we started asking them to provide some voltage support services, frequency support services. Sarah, you mentioned this, things are very important for grid reliability. And so technology stepped up, and now it's kind of mainstream that wind solar storage provides frequency support, provides voltage support, oftentimes with characteristics that are much more controllable and can be designed towards the grid's needs easier than with traditional synchronous generation, just because all of that is controls and software and kind of technology can easily adjust to what the grid needs are. And then we progress even further to maybe like 50% of inverter-based resources. We start seeing even more essential reliability services going away. Then we need even more support features from inverter-based resources. Maybe some of them are now providing reserves and faster frequency control. You mentioned, fast frequency response. This is something that becomes necessary in batteries, and solar resources are very suitable for that. And then we progress even further. Rick, you mentioned, you're probably ahead of me. Last I heard was beginning of March, ERCOT hits 76% of instantaneous penetration of inverter-based resources. But March and April are, times very rich on wind and solar. So maybe that number is higher now. But basically, yes, you reach 70 to 80%. You start getting to the point where need for certain essential reliability services becomes very urgent, and you need more capabilities from existing resources on the grid to provide this need. And so this is where we start talking now, and I'm not sure, Sarah, if you have this term in your glossary, but grid forming, you may hear this term, and these are advanced controls for inverter-based resources, wind, solar storage, even though like storage is more suitable for this technology, but they can basically provide the suite of reliability services that synchronous generators are providing today. With that technology, you can potentially go to 100% instantaneous inverter-based resource penetration, and it's been shown in smaller islanded systems that this is possible, and also in large scale system studies. So I mean, from technology perspective, what I want to say is just as the grid evolves and we define what the grid needs, we define it in technology neutral terms, technology will step up and provide. And so there is technology today to essentially go to 100% IBR. So I think I'll stop at that and we'll take the rest during Q&A.
Amazing. Thank you so much, Julia. And I believe we do have grid forming defined in our glossary. So shout out to that glossary. And thank you so much for those really helpful remarks. So yeah, now we'll turn it over to Wilson to hear a little bit more about kind of what we need to do to get kind of closer to those 100% clean energy penetrations in terms of, what that kind of final 10% looks like. So Wilson, over to you.
Thanks, Michelle. And yeah, I'm going to be kind of zooming way out and looking at the much longer term technology mix resource adequacy question, and discussing how clean technologies, both the ones we have commercialized today and ones that are currently in their development phase, can contribute to ensuring that we have as much generation as we need, regardless of demand or weather conditions. And I want to be clear that the technologies that are currently experiencing widespread commercial adoption, wind, solar, lithium-ion batteries, can actually go a long way towards ensuring that system-wide resource adequacy. One of the best examples is just that in many grids around the country, peak demand is hot summer days, and wind and solar and batteries can meet that demand extremely reliably and reduce the need for other forms of capacity in the system. But as we increase utilization of these technologies and they become a larger and larger part of the system, the most difficult periods eventually start to shift from those when demand is highest to those when wind and solar output is lowest, because these resources are self-correlated. And battery storage can reduce the severity of this issue, but current batteries are not necessarily a cost-effective solution to very long periods of low wind and solar output. And so there's a whole suite of emerging technologies that are designed to help fill these very rare but important gaps and ensure a 100% reliable, clean system. One class of technologies is long-duration energy storage, which is kind of poorly defined, but in general, it's described storage where the amount of energy you have in storage is much less of a limitation than it is with, say, 4-hour batteries today. And so, these storage devices are still technically energy limited. You can't discharge them forever. But if you have 100+ hours of capacity, that's barely a distinction worth worrying about in many situations. And so technologies that maybe have lower efficiencies round trip than lithium-ion batteries, or are worst at kind of fast burst discharge. These batteries are very good at these short-term reliability services and cost-effective capacity. But technologies that are maybe worse at those aspects, but on the other hand, have really, really cheap storage capacity where you can add megawatt hours for basically dirt cheap compared to lithium ion. That's your canonical long duration storage technology. And things like hydrogen storage or emerging metal air batteries are really good examples of those. Alternatively, there is what we would call clean firm generation, which are power plants that can provide low carbon power that is available indefinitely whenever needed. And these are technologies that will always likely be more expensive per megawatt hour generated than wind and solar. And so you probably wouldn't expect to want to use them for the vast, majority of total megawatt hours used in the system. But the value they can provide and the timing of their generation can help drastically reduce system costs. And we see this repeatedly in system modeling exercises where including some clean firm in the mix is really important for ensuring a reliable and cost-effective low carbon system. And technologies in this class could be nuclear power, which obviously has been deployed in the past, but is not currently being deployed large scale in the US. And there are kind of emerging next generation nuclear technologies out there currently undergoing development. Next generation geothermal is a big one right now. Fossil plants with CCS and biomass could also potentially fill this role. But one common characteristic of all these technologies is that they lack significant ongoing commercial deployment. They're all still kind of where solar, wind, and batteries were a decade or more ago, where they are, early stage in the demonstration phase, potentially high cost, but with the potential to come down in cost greatly as commercialization scales up. And many companies are already planning or undertaking early stage demonstration or first of a kind commercial projects due online in the next few years to the next decade. And so ensuring the success of at least some of these projects is going to be crucial to ensuring the availability of a portfolio of clean firm resources that we're going to need for a 100% reliable, as high percent clean as we can achieve system in the long run.
Okay, great. Thank you so much for that overview, Wilson, on how those kind of clean firm and long duration storage technologies fit in with this broad portfolio of resources that will be needed to reach those really high penetrations of clean resources on the grid across, the whole grid. So that was really helpful. And I'd love to jump into some questions for our panel now. I know that we have a few questions coming up in the chat. We'll hopefully have some additional time for those at the end, but if our panelists are seeing things come up that relate to them and, it's not too distracting to answer, feel free, but we can also try to answer some of those after some of my questions. So, my first question is, a chapter in our report was really focused on how demand side resources can help contribute to reliability, both kind of on a resource adequacy perspective, meeting those peak times, and also in particular, helping us do it more quickly and cheaply than some supply side resources. So I'd love to start by asking our panel, how can demand side resources contribute to reliability? And why is it important that we focus on them? So I'll start with Rick.
Awesome. Thanks, Michelle. Yeah, this is a great question. And I think I sort of touched on it a little bit in the intro. So it's really important, to be clear, like our system's always been pretty peaky. We've always had, we don't have load that's sort of flat. And as things change, especially as we move towards like electrification of space heat, we're going to have some more times like in the winter. Like I think we're really seeing our grid get stressed in the winter. And that means we just have, there's like a handful of winter mornings, like especially in the Southeast where we have these big peaks. And in many cases, it doesn't really make sense to sort of build a power plant that is really only going to run for just a couple hours a year to address those like handful of peaks. It's actually a lot smarter to then bring in demand side resources and flex the load. So I think it's really important to think about that. And I also just sort of think that the technology that we have access to now is just a lot easier to do this kind of demand flexibility for people that have been around for a long time. 20 years ago, we tried to do this, but it was hard, it was complex, it required, kind of custom hardware and software, and utilities would do things like put a box on your air conditioner and with a radio to talk to it. But now people have internet in their homes, like it's a lot easier to do demand flexibility. And then I just want to give a shout out to a recent report that came out of the Duke Nicholas School. Tyler Norris was the lead on this, and he really looked at like just if data centers could flex just a little bit, right? So sort of like 0.25% of the hours a year, we could add 100 gigawatts of new load to our existing system without building new capacity. So you can really see that flexibility is incredibly powerful, and like we can do a lot with just a little bit of flexibility. I still think there's a lot of regulatory and just kind of institutional barriers to unlocking this demand flexibility that we need to address. But I think that Nicholas report really just shows how powerful demand flexibility can be.
Yeah, Julia, did you want to go ahead?
Yeah, I wanted to add on two sides. I think Rick touched on resource adequacy side of things, and maybe more on like hour-to-hour flexibility. I wanted to talk about reliability side of things. So demand can provide very good frequency support type of resources, and ERCOT is a good example for that. So since 1996, I think they allow provision of frequency support service from large loads, for industrial loads. So these are not data centers, but like petrochemical loads of sorts of different types. And so by now they provide more than 50% of frequency responsive reserve to the grid. So like 50% comes from generation. A lot of it is battery now, but also 50% from load. And it's been very effective, and it's a good business for them. They are really careful about being there and responding when needed, because that's a good participation for them as well. Provides income stream for them as well. And the other thing I wanted to mention, I think it's maybe not quite addressed yet, as we start looking at resiliency and weather conditions, right? There are extreme weather conditions that are happening. We're still looking at, resiliency is an ability to, be able to serve load, to be able to ride through, but there are loads that are not essential. And I think in our world with, of internet and smart metering and all of that, there is something we can do on load shedding side and on this, rotating load sheds that operators normally do. We can wire more non-essential loads, and with that save on building new units that only operate maybe once a year for an hour. And I think that's something where more research is needed, and we are not really looking into that right now. There is a lot of potential there.
Awesome. Thank you so much. Yeah, go ahead, Wilson.
Yeah, I just want to add briefly to both those great answers and say that there is, in addition to just the flexibility and reliability benefits, there are huge economic incentives to unlocking demand side flexibility. There a very, very large portion of total system cost goes into just meeting those peak hours. And so anything we can do to reduce demand is both going to unlock headroom, make the system more reliable, and drastically reduce the cost that everyone pays for all the rest of the hours we consume power.
Yeah, I think that's a great point. And yeah, so thanks so much for all those perspectives. My next question is on trying to tease out some of the subtleties behind some kind of buzzwords that we hear a lot for reliability, particularly dispatchable and baseload. So I'm wondering, Wilson, if you can kind of help the audience and kind of me understand really what these terms mean and how sometimes they may be misused in kind of reliability speak and what we need to be focused on there.
Yeah, happy to. So these are terms that get thrown around and I think conflated all the time, and they are not the same. Dispatchable is, I think, the really key term when it comes to reliability and resource adequacy. That's the one that has a lot of meaning. It essentially just means that you can get as much generation from these facilities as you need or as they can provide whenever needed. So you can control their output. You could describe resources that are not weather dependent as dispatchable. You could describe resources with enough energy and storage, like large hydro facilities or long duration energy storage facilities, as dispatchable. And the role that dispatchable resources can play that's key is to fill in any gaps when there's either very high demand or very low wind and solar output. Baseload is kind of a subset of dispatchable resources, but it essentially just describes things that generate all the time. And there's a lot of people going around saying we need baseload. And it's true that baseload generation is an important part of the grid today. There's a kind of, it relates to literally the base demand in most grids where there's a minimum amount of demand. And so there's a certain amount of generators that you can build that are just always on and always serve that base demand. And that's traditionally been a very, you know, a typical role in the system. Things like coal and nuclear plants have filled it. But going forward, baseload isn't necessarily what we need, at least in all conditions. In places like California, we have more solar power than we even can use during the middle of the day, many days. And so we're getting into a situation very rapidly where we don't, in fact, need power generation all the time. At specific times, power is very abundant, very cheap in some hours, and very scarce in others. And so the best resources in those cases economically are generally those that can provide that, again, dispatchable generation when it is most needed and most valuable at least cost. And baseload resources may have a role in filling that need, and they're likely always going to play a part in electricity systems, depending on the geography. But baseload has not been a panacea in the past. It's only one portion of our grid. We still have fluctuating demand, and baseload generators don't meet that. And it's certainly not the end-all be-all of reliability going forward.
Awesome. Thank you so much. I think what I heard there is that both dispatchable and baseload are characteristics of certain resources, and they don't necessarily mean reliable in and of itself. So thanks so much for that. So my next question is just, Rick, you talked a little bit about how Texas is achieving very high penetrations of clean energy on the grid today. So I'm just wondering if I could hear from the panelists on some specific real-world examples of how clean and renewable energy is providing reliability today, both on the resource adequacy and operational side of things. So maybe I'll start with Julia for this one.
Yeah, and I maybe use ERCOT as an example. My main experiences from there, as I mentioned, they did achieve 76, maybe beyond that by now, of penetration of inverter-based resources, wind, solar, storage in any given point in time. From 2012, I believe, if I'm not mistaken, wind and solar are required to provide frequency support. And so they all have capability. It's always on. So whenever there is a frequency event on the grid, storage was a little bit later. So now wind, solar, storage, all of them will provide response. So if a large generator trips, frequency starts declining, all of the resources that have headroom to respond will respond. And oftentimes, like now it's 76%. If you look at what was available, I'm pretty sure that they could have had more on the grid, but there were some limitations, maybe transmission limits that didn't allow all of the wind and solar generation to be extracted. And so what it means is that even solar and wind is sitting there and they have headroom. And so they can provide frequency response to the grid when generation trip events are happening. So I mentioned grid forming, not yet in the US, but in some other regions around the world, grid forming now is providing services like inertial support and system strength support, so like making systems stronger, going back to the slide that I had. And so there is this technology as well with these resources can in a very short time frame provide essential reliability services that synchronous generators have provided previously. And so that's being deployed in Australia, in Hawaii, and more recently in Great Britain as well. And so we're looking now, so currently in ORCAT and MISO, I know SPP is looking at that. All of them are looking to require grid forming capability from future batteries. And so that is to provide initially grid strength support, but also going forward, if inertia becomes an issue, then also support inertia and frequency.
Awesome. Thank you so much. I wonder if maybe Rick could talk a little bit about how clean energy can provide capacity in various grids around the world. I know we talk a lot about the need to meet peak demand and how, as we discussed, a lot of renewable energy is weather dependent. So how can clean energy contribute to those peak demand moments?
Yeah, well, I think when Sarah was sort of introducing the whole webinar, she did a great job of talking about the portfolio of resources, and I think also, again, not to keep talking about Texas. I mean, I clearly am a big Texas fan or at least of the Texas grid. A great example is sort of this portfolio of resources. So wind plus solar plus batteries really can provide the capacity we need. With the caveat, of course, like I think Wilson actually did a really great job of sort of talking about the need for clean firm, right? So that's, still needs to be, we still need something that looks like today's peaking natural gas for times when we don't have wind. But as these grids are the way that we forecast out a couple of days to understand, like, okay, what is the wind going to show up? Is the sun going to show up? Do I have enough resources to put the symphony together? So I think it's a great, the grids that I talked about, SPP, Texas. I think we can also talk about California that Wilson mentioned, really with like a lot of solar, a lot of storage, but then also other resources. And I think that's really kind of the answer, right? And it's going to be dependent, right? So the Northeast is going to rely more on offshore wind than Texas is. But we can put these portfolio of resources together to really provide. And I think the story is pretty strong, right? Last year SPP was almost 50% carbon free. California was close to 60% carbon free. Texas was over 40% carbon free. So like these are pretty big numbers, right? These are numbers that I'm old. I've been doing this for a long time. 20 years ago, people were like, "Oh, we can't do that. We can't do those kinds of numbers." So I think we can continue to increase those percentages. And I think it's also interesting to point out, and I'm just looking at like some of the questions in the chat, that there's the grids that are most concerned with this, right? So I think about the largest grid in the country is PJM, is very concerned about meeting load with clean energy, and they sort of are sort of feel like they really the only answer is gas here. PJM is like in the single digits in terms of its wind and solar percentage, right? So I sort of point to these other grids and I say, but look here, look at what SPP is doing, look at what Texas is doing, look at what California is doing. And so I think it's just really an education and like a comfort level that planners and operators really need to like understand that they can do this. And these other grids have been doing it for a long time. So
yeah. And Sarah, did you want to jump in too?
Yeah, thanks. I just wanted to make a quick point about timing. And there are a few questions in the queue relating to more recent conversations. Yesterday, there was a hearing. The Energy and Commerce Committee held a hearing on this very topic, and agree that the kind of general consensus was like more gas, more gas, more gas. I think there needs to be a bit of a reality check on how quickly we can get new gas built. And the facts of the matter are not for about 5 years. So if we have a concurrent, call for energy now, immediately, and we think that the only solution in our mix is gas, then those are very at odds with one another, because there are supply chain shortfalls, there are long-term permitting and just general construction timelines that have to be negotiated with gas that, certainly wind and solar and batteries also have longer timelines, probably longer than they should, but they can be built relatively quickly. And per the other comments made, demand side resources are another tool in the toolbox that actually can be deployed very quickly if we allow them to scale and if we allow them to become visible on the bulk system grid and really tap into their full potential. So we're sort of talking at odds with one another with respect to what we need and what we can do, but there's a whole mix of resources in the middle of that that actually provide the solutions that we need to meet the challenges of the day. So just want to make that point.
Thanks, Sarah. And yeah, I'm excited to see we have more comments from our panelists. So I think Julia's hand was first. So do you want to go ahead, Julia?
Yeah, I just wanted to add to what Sarah was said. I think it's not apples to apples comparison though. So if you're looking at, how you say 5 years to build gas-fired power plant, you are looking at just like what technically it takes, right? When you're saying it takes much longer to build, not much longer, but it takes comparable time or maybe longer to build solar and storage, it's more of a policy, a regulatory policy decision. I think it's like if you compare to ERCOT, it takes 2 to 3 years to build wind, solar, storage. So they come very fast. And this is just because the way how the transmission issues are decided. Transmission is built kind of holistically for the entire system and not assigned to each generator or cluster of generators separately, how it is done elsewhere. And it's not causing a queue backlog similar to other places. So this is kind of a policy regulatory issue, whereas technically it does take 2 to 3 years to build solar storage, wind. So if we solve that problem, we can actually get this generation online much faster. I just wanted to add that.
Thanks very much. I totally agree. Wilson?
Yeah, I kind of want to follow up on Rick's point a bit about how there are some places that are, kind of throwing up their hands and saying gas, gas, gas is the only solution. And there are other places that, are actually doing very well at integrating renewables while growing demand and, contributing to both energy and reliability and capacity. And I think part of this ends up being less an issue of engineering and actual physical reliability and more a challenge of planning and the sophistication of planning processes. I mean, there are some places in the country where, and PJM doesn't fall into this category, they're a bit more sophisticated, but there are some places where people are still planning system investments in Excel sheets where it's essentially impossible to understand how something like solar or wind or batteries, for example, can contribute to the reliability of your system. And so in that case, you do just maybe have to throw up your hands and say, well, gas can probably do it. But if we can get better, and I'm a modeler, I'm going to plug some models here, but if we get better on the kind of system modeling and planning processes where we can really say with confidence that yes, contribute this much wind and solar can ensure reliability over any sort of conditions you're liable to experience, that's going to go a long way towards enabling those sorts of deployments.
Yeah, I think that's a great point. And to both Julia and Wilson's last points, as we've heard, we have a lot of the technical components that we need to be able to undergo this transition. And a lot of the barriers are more on the policy side, on the regulatory side. So I think we have a few questions along these lines in the chat as well. But for each of the panelists, what in either the short term or the long term is needed to make sure that these resources are able to effectively compete in markets, are able to come online quickly, et cetera. So I don't know if somebody wants to start on that, or I can just Rick's faces. Maybe Julia, maybe I'll call on you to talk a little bit. Just, I know you just talked about the importance of speeding up the interconnection queue, but is there anything like specifically for inverter-based resources and making sure that they are, able to compete in the markets that are needed on the kind of operational reliability side, less so on the getting them through the queue side?
I think it's what Wilson said. It goes to any kind of these three pillars that you were showing. It's if you do your studies diligently and in a sophisticated way, looking a few years out, you define what system needs are in as technology neutral terms as needed as you can. Things that you can procure through markets, define market products, procure them through markets, things that kind of like maybe locational or maybe all resources need to provide, those need to go into interconnection requirements. And so if you put them clearly and in a timely manner, technology will step up and will be able to provide from inverter-based resources. I think we have like 30 years of experience now with inverter-based resources going from no services at all to now replacing essential reliability services from synchronous generators. So I would say this is what it takes, like study well, define well, and then they will come. The only kind of word of caution for, I understand we have policymakers on the call, is don't distort market, kind of like don't let your, being afraid, like you mentioned PJM, being afraid of operating a certain way, don't put products that distort how market works itself, and like favoring one technology over the other just because we believe it's more reliable. It can actually do more harm than good and make it more expensive in the long run.
Thanks so much. Yeah, just focusing on the kind of data and science behind it, I think would go quite a long way. Rick, you came off mute. Do you want to add anything, or was that just?
No, I just want to I just want to say that what Julia said is perfectly right. I think as you asked a hard question, but I think the easy answer is really like a technology neutral platform that allows supply side, all supply and demand side resources to compete fairly is the perfect answer.
Awesome. Well, great job on having a perfect answer, Julia. So we do have a few great questions in the chat. So I think maybe we'll kind of spend our last few minutes going through some of these audience questions. We have a couple of kind of specific, well, okay, maybe I'll ask this one first. There's a question in the chat about can battery storage be considered dispatchable? So maybe I'll ask this one to Wilson first. Oh, well, Wilson and Julia. Go ahead first, Wilson, and then we'll hear from Julia.
Yeah, I guess I'll say it's a spectrum. It's, you can have battery storage that can only discharge for 1 hour, and you can have battery storage on grids today that discharges for up to 4 or 8 hours. You have pumped hydro that can be many, many more hours. That's kind of long duration storage that's currently on our grid. And then you can think about these next generation technologies that could discharge for hundreds of hours potentially. And so, some of these things might be dispatchable in the sense that you can choose when to discharge that power, but they're energy limited in the sense of how long you can, actually do that feasibly. And so when you think about reliability, the dispatchability is important, but for storage, when you really get into very high renewable penetration systems and ones where those kind of long renewables droughts are the most important periods for reliability, that's when storage duration starts becoming really important.
Awesome, thanks. Julia, did you want to chime in?
Yeah, I wanted to chime in when Wilson was talking about dispatchable first time, and since somebody asked, I want to chime in here. So I think solar and wind are dispatchable. So I think we need a third term here. So dispatchable is something that, Wilson, you said, is something that can be moved in real time. And so solar and storage and battery, they all can be moved in real time as is economic for the market at the given moment. I think we need a third term for something that is have available headroom on demand, and maybe it's some kind of like backstop generation or whatever you want to call it. But and that is like very low percent that we need in the last, like as a last resort. All these other resources are perfectly dispatchable. Baseload is not dispatchable. So we have nuclear units in this, like in the US, I know they are not being dispatched. They just sit at the maximum all the time. Everything else is dispatchable.
Thanks so much. Yeah, I think that's a great distinction. There's this question of like, can it be moved up and down at all versus can it be moved up and down at any given time?
And if it has headroom, yes. Yeah. And coming back to the headroom, like if a wind unit or solar unit is curtailed, it actually has headroom and can be moved up if needed.
Mm-hmm. Okay, this is another kind of more specific question, but kind of getting into the specifics of how inverter-based resources can provide grid services. Can inverter-based resources provide the reactive power and black start services needed to ensure grid reliability?
So reactive power, yes, from get-go. I mean, there is a fork order that requires to have capability. There are local interconnection requirements that for many years now require reactive capability. So yes, all inverter-based resources can provide reactive power and really superb voltage control when designed correctly. And for black start capability, that requires specific design consideration. Grid forming resources only can be black start capable. There are actually real life examples where grid forming batteries are being used to start gas turbines, and then gas turbine serves as a kind of like black start unit. But even on its own, they can do that. The only thing, again, is design consideration. It has to be grid forming, and it has to have enough storage capacity and sufficient state of charge to do black start.
Got it. Thanks so much. And I'll just end it off with this kind of more high-level question. Congress had a hearing yesterday about grid reliability where they brought every head of the grid operators in the United States to come testify before Congress. And yeah, so I'm just wondering from any or all of you, maybe we'll do one from each of you. What is maybe one top takeaway that you would offer to Congress on grid reliability on the best way to maintain both reliability and affordability right now?
I'm happy to start, Michelle. Yeah.
Awesome.
So I think the number one way is to really like let is what we already talked about before, which is really, fix the interconnection queues, let all the wind and solar and battery storage projects that have been sitting in queues. We have 2 terawatts, like more than all the generating capacity in the US, waiting to connect to the grid. If those resources could connect to the grid, we could provide all the energy and reliability that we need to meet the surging demand. So I really think that's sort of the first thing is like, why are all these things stuck in the queue waiting to connect? Let's get those built. Now I'll let my other awesome panelists give better answers.
I would say, again, kind of going back to defining what the grid needs, monitoring online, maybe something we haven't talked about is monitoring online a few hours ahead, what you have, and operators taking actions and having this visibility, having measurements from all available resources, loads including, will take us a long way on reliability side.
And I'll just say that diversity of resources is a strength, and there's never been a one-size-fits-all solution to a reliable grid, and there isn't now. And any kind of policy, simple policy solution where we just have to build X is not a good response to what is a very complex system with diverse needs and a diverse set of resources that can kind of cover each other's weaknesses in a way. And so anything, I'm kind of looking at Texas here, but like proposals that basically say we're just going to, maximize X are probably sending us down a very costly and potentially risky path.
Thanks so
Michelle,
much.
can I add just one more thing? I think we're completely overlooked. We haven't mentioned transmission even once today, but I think that's another one that where it can offer reliability, connecting resources and loads that are already providing reliability and kind of leveraging across wider areas than just local provision of reliability services. So transmission, we need that for sure, higher voltage and across the regions.
Yeah, definitely. To that point of the most reliable grid is one that has a diverse set of resources available. Transmission really helps us access that diversity too. So thanks for pulling transmission into this discussion, Julia. Awesome. Well, I think we're at time. Thank you so much to all of our amazing panelists and this wonderful audience for all of your great questions. I hope that we can follow up on some of the ones that we didn't get to today. Sarah, any final words?
Just wanted to say a huge thank you to our panelists again and for the experts that we drew on for our report. And, maybe a final takeaway note is just be scrupulous. Anytime someone is oversimplifying the topic of grid reliability, take a moment and refer to our report and the other excellent resources out there and educate yourself a little bit more about these complex topics. And we can hopefully have a more informed and productive discussion on all of these topics going forward. And with that, we will close out the webinar. Thank you all so much, and we will share the recording after the fact. Thank you. Bye.
Yeah.
Thanks, y'all. Good job.
Thanks, everyone. That was awesome.
Thanks. Nice job.